Thank you very much. So I'm going to be talking about a model for imaging cortical microstructure, cortical layers in humans in vivo. And there's been many recent attempts. It's been an increasing challenge of the field of MRI to image the cortical layers. And there's been many approaches to this and varying success. And as far as talking about the in vivo imaging on a whole brain basis in humans, there's only been limited success. But one of the approaches to this task is by segmenting the cortex based on the T1, because T1 is sensitive to tissue properties, and different cortical layers are composed of different, have different cytoarchitecture, myeloarchitecture, glial content, so they may have different T1 and may be separable based on this. And here you can see a quantitative T1 mapping of the brain. You can see that there's a gradual decrease of T1 from the outer surface into the inner surface of the cortex. And this is not just because of CSF partial volume on the outer surface and white matter partial volume in the inner surface, because when we look at high resolution ex vivo imaging of rat brain, we also see this pattern inside the cortex itself, inside a gradual decrease inside the gray matter. So going back to the T1 mapping, if we take a look at the whole at the cortex T1 distribution, you can see that there are several peaks there. So the cortex may be segmentable with simple clustering, and as you can see in this example with k-means based on these peaks. And this looks like quite a good segmentation, but there are still some issues with this approach and with any whole brain approach to imaging the cortical layers. And this is mostly because of partial volume issues. So the cortical layers, some of them are only 100 microns thick, so you need really high resolution, which is a challenge. And even if when you attain such high resolution, the convolution of the cortex, as you can see in this crude example, ensures that we'll have partial volume issues even in higher resolution. And by partial volume, I mean more than one layer inside the voxel. And so this is an issue. So you essentially need a much higher resolution effectively in order to resolve this issue. And so maybe image resolution, increasing the image resolution is not the answer in this case. And we have been attempting to, because we want to image the cortical layers on a whole brain basis in clinically feasible times, we want to find a different solution, and it's not working. Okay, so and the solution that we have been looking into is to go beyond the voxel, and which means breaking down the voxel into the tissues that comprise it. And in this way, modeling the partial volume effect. Not only both the CSF and white matter partial volume that occurs, and the partial volume of more than one layer inside the voxel. And in order to do that, you need to increase your T1 resolution, which requires more scans. So here on the left, you can see the T1 corticogram from before. It's from regular quantitative T1 mapping. It takes, in high resolution, it takes about 50 minutes. And on the right, you can see the whole brain T1 distribution from a low resolution protocol where the analysis is a multi-compartment analysis, meaning breaking down each voxel into sub-components. You need 60 scans, but it only takes 12 minutes. And you can see that the pattern of the peaks is quite similar. The values are different because we're modeling, on the left we're modeling voxels, on the right we're modeling subcomponents, but the pattern looks quite similar, and we wanted to use this as the basis for identifying different gray matter distributions in the brain. So in this project, we have 66 subjects so far, and again, we used 60 inversion recovery scans with inversion times between 50 and 100 milliseconds, but with a heavier focus on the gray matter range, which we were interested in modeling. Again, low resolution images, which means high SNR and very fast scanning times. It's only 12 minutes for whole brain acquisition for the whole protocol. And what we did is, instead of fitting each voxel to the regular inversion recovery equation. We fitted it to a modified multi-component T1 equation for each voxel, where we break each voxel down again to its components, each with its own T1 and volume fraction of the voxel. And so here you can see an example for a single voxel. The curves look quite similar, but they have a different number of components. So for example, the orange one has one component, the blue one has 6 components, and if we zoom in here for a second, you can see that they model it a bit differently. And we used the mean squared error of each of the fitting for different number of components to determine what is the optimal number of components per each voxel. And after doing this on a voxel-by-voxel basis, we could get, again, the whole brain T1 distribution of components. And we wanted to identify the different gray matter distributions. And in order to do that, we used a mixture model, a mixture of T distributions, because they're more robust when estimating noisy data than normal distributions. And you can see here an example for a mixture model with 8 mixture components, and we want to determine the optimal number of mixture components. So we examined the Bayesian information criterion. The lower is better, and here we're looking at the negative log of the BIC, so higher is better. And you can see that it changes as we add mixture components. But we found overall that 14 mixture components was the optimal number. It was quite robust across all subjects. And then we wanted to identify gray matter mixture components. So if you see this arrow, this is the mixture component on the right. So you can see it has a very low probability in the cortex. And as we continue along them, we have some what look to be CSF mixture components. And here we get to what we found was a gray matter dominant mixture component. So we call this one T1 layer 1, and we have T1 layer 2 and T1 layer 3, and again T1 layer 4, T1 layer 5, and here we have T1 layer 6, and then we found some white matter dominant mixture components, but overall we found 6 mixture components that were gray matter dominant, and they were also in the range between 800 and 1800 milliseconds, which is what we would expect the T1 of gray matter to be. And if we look at the box plot of the mixture centers for all the subjects, you can see in the gray matter range that this is quite stable across all subjects. I want to stress here before I move to the next slide that the numbering of the layers, layer 1, layer 2, layer 3, is slightly arbitrary. We're simply because as I showed earlier, the T1 decreases from the outer edges of the cortex to the inner surface, so we numbered them 1 to 6 from the higher T1 to the lower T1. This does not mean that they actually have a high correspondence to, for example, the cytoarchitectonic layer 3 or layer 4 and so forth. And from here, it's very simple to calculate T1 layer probability maps using Bayes' formula. And for each subject, we then registered the probability maps to an MNI brain that was parcellated into 1,000 cortical columns in order to perform spatial analysis that is not bound to the voxel. And you can see the results here. You can see they vary across the cortex, but you can also see some interesting patterns. So you can see that, for example, it's quite symmetric between the right and the left hemisphere. And you also, if we look at the visual areas in the occipital lobe, you can see that they have quite a unique T1 layer composition. And we also know they have a unique cytoarchitectonic composition. So this gives us confidence that we're measuring some form of microstructure. And here we can see on the left are the results again, the same results I just showed you. And on the right is the standard deviation between subjects. Note that the color scales are different, and the variance between subjects is quite low, again, showing that this method is quite reliable. And we believe that this method can have several advantages, and one of them is that it gives you whole brain information. So you're not just focusing on a single area in high resolution, like the stria of Gennari in area V1, you actually can do this on a whole brain basis and perform comparison between groups based on their microstructural composition. It's very short, only 12 minutes long. It's a very simple protocol that can be reproduced in every scanner, and it can be combined with various other methods. It also has some limitations that I wanna discuss. So first of all, it's a probabilistic method. So I can't point at the single location in the cortex and say, here we have layer 3. I only get probability maps. Due to the low resolution nature of the scans, it's a limitation. I can't, you can't use this protocol in high resolution. It's not feasible. And also there's only a moderate correspondence to histological findings. Again, we call them T1 layers. It's not one-to-one or as the same as the cytoarchitectonic layers. And, but we believe that this can be used to not only investigate cortical microstructure in vivo in humans, but to also identify a relationship between that and cognitive functions, traits, and maybe even pathologies and neurodegenerative diseases. I want to thank everyone who contributed to this project, and thank you very much for your time. And well, it said come visit me at poster 2510, so hopefully you'll do that. Thank you very much.